So welcome. This is now week 6, and this is lecture number 10, because we did not have a lecture last Thursday, which was the exam. So we are now on lecture number 10, Math 140 SCI, and this is October 5th. So we are on section 9.4. Randomized comparative experiments. So what is the definition of a randomized comparative experiment? It's an experiment that uses both comparison of two or more treatments and random assignment of subjects to treatments. Okay, so an experiment that uses both comparison of two or more treatments and random assignment of subjects to treatments. So what's an example of a randomized comparative experiment? Well, there's lots of them, of course, but pretty much anything that the FDA does. When the FDA is testing, or if anyone's testing a new drug and they wonder if the drug is working or not, what do? You assign the drug to a group, and then you assign a placebo to a control group. So you have multiple treatments. Thank you. Multiple treatments, but how do you decide who gets what treatment? Well, that's where the randomness comes into play. You're comparing multiple treatments, but at the end of the day, who gets what treatments is completely random. Reminds me of that Grey's Anatomy episode where Meredith switched the treatments because she wanted someone to get the real drug, and it caused a whole to-do. Everything important.
What season was that, Professor?
What season? Oh my God, I don't know, 7 or 8. It's been so long. I don't know. It was when Adele was still alive. That was Richard's ex-wife.
Oh yeah, she died.
I know. It was horrible. It was a long time ago. Did you just laugh that I watched Grey's Anatomy? Spoilers, it was like 10 seasons ago. 10 seasons.
I'm on season 5.
Oh, sorry. My bad. Spoiler alert. Yeah, I guess that was bad. Sorry. Luckily, it wasn't a major character. I'm not going to go into the important ones. Oh, Lexi. Okay, so next. This is what a randomized comparative experiment is. So what is a completely randomized design? What is a completely randomized design? Okay, it's any method, whether good or bad, but any method that assigns treatments to the subjects randomly. Okay, the design is how you go about assigning treatments to the various subjects. You always need some design to do it. There's not a lot of math here. This is just, conceptual. What will be one method, by the way, of assigning drugs randomly? What's one method that I can use?
A random number generator?
A random number generator always works fine. Yeah. A random number generator always works fine. Okay. So again, that's it for 9.4. No math in there, just a couple definitions. In total, in the section, I count 1, 2, 3, 4 paragraphs. Very small sections, not a lot of information. 9.5 is actually a more important one. Okay. The principles of experimental design. Principles of experimental design. When you design an experiment, there are certain aspects of it that you should always have in mind, upon which you're basing the experiment, what makes an experiment a good experiment. The first one is control. What do I mean by that? Restrict the effects of any lurking variables on the response. If I want to determine whether a drug works, for example, then any other factors which might influence the success rate, the healing of the patients, that may not be attributed to the drug itself, would be a lurking variable. Maybe the patient is exercising more. Maybe the patient is taking some Tylenol along with the drug. Maybe the patient is doing this. Maybe the patient is doing that. When you want to determine whether something has the effect that you're hoping for, you want to limit or remove any factors which may play a role so that you can isolate the contribution of your explanatory variable. It seems very logical, correct? Very straightforward. 2, randomization. Randomization. Okay, which is obviously, we spoke about randomizing a lot, but it's using chance to assign subjects to treatments. Don't pick and choose based upon who you want to get the real thing, or who you want to get this treatment, or what they're wearing. Do it solely upon randomization. And number 3 is replication. Use enough subjects to reduce chance variation in the results. If I just test one patient and they happen to get better, can I reasonably attribute that to the drug that I gave them? Or might they have gotten better on their own for whatever reason? If I do it to 1,000 patients and 998 of them get better, then maybe I have something to work with, right? So replication, the more times you do it, the better your analysis is going to be. That makes sense? Now, suppose I'm interested in I'm a wood carver. Okay, it's a little hobby of mine. And I carved dice, and I carved a 1, 2, 3, 4, 5, and 6 into the 6 size. And I am interested in whether or not my dice is fair. So how can I determine whether or not the dice that I just made is fair or not? What's one thing that I can do? Anyone, what's one thing I can do to determine if my dice is fair? This is for everyone, by the way. So feel free to, you know. Feel free to
Just
go
like
ahead.
roll it,
Yeah, roll it and do what? Roll it, what, one time?
like maybe 6 times.
6 times. So if I roll it 6 times and I get one of each number, can I conclude definitively that my die is fair?
Yeah.
There's no possible way it could have happened one of each just by chance alone. Let me ask you a question. You ever roll a real fair die and get the same number 6 times in a row or 5 times in a row?
No.
In your life, that's never happened. That's never happened in your whole life. You're telling me you've never rolled a die, like 5 dice, rolled them all and gotten the same number 5 times. That's never happened in your entire life.
It wasn't weighed, so no.
Really?
If it was weighed, then it would.
I'm not talking about what might happen. I'm asking, I want you to think back to your entire life up until this point. Have you ever rolled 5 dice or 4 dice at the same time and coincidentally happen to get the same number every time? Okay, but Flower it's happened to. It's happened to me. I see Leanne nodding. So some of us it's happened to. Okay, playing Yahtzee. Oh my God, Yahtzee. Wow. I remember that game. I don't remember how to play it, but I certainly remember it. Yahtzee. Anyways, the point is that sometimes results can occur which are not common, but if you do something often enough times, rare events occur. That's life, right? Getting hit by lightning twice. It happens. Okay, it happens. It's rare, but it happens. Rare events occur. When something occurs, you have to ask yourself one of 2 questions. So this is important. When some event occurs, you should ask the following question. You should ask, did it occur by chance? Did it occur by chance? Or is it such a rare event that the only way it could realistically occur is by design? Like, for example, if I roll 2 dice, just 2 dice, and I get the same number, I'm not saying it happens often, but if it did occur with 2 dice, would you say it was a rare event that occurred, or that the dice must be weighted because there's no way that would have happened otherwise?
It's a rare event that occurred.
Okay. What if you flipped a coin 100 times and you got 100 heads? Okay, you flip it, you got a head. Flip it again, a head. Flip it again, I got a head. Would you say Well, anything's possible. I mean, I can get ahead 100 times in a row. Or would you say, this is such a rare event that the only way it could realistically occur is if the die or the coin is weighted, or maybe it's a two-headed coin or something like that. What would you claim if you rolled a head or flipped a head 100 times in a row? Which of those two? Is it possible that it could occur on a fair die? It's possible. Probably weighted, right? By the way, do you have any idea, if I asked you for homework to flip a coin until it occurred heads 100 times in a row, a fair coin, how long do you think it would take before that occurred? If I said, here's your homework, just flip this fair coin, here's a quarter, flip it until you get heads 100 times in a row. How long do you think that will take?
Forever.
A really long time.
You know how long it would take, realistically? Longer than the age of the universe. You could flip a coin over and over again your entire life. Luis, you say 20 minutes. That's your homework, Luis. I challenge you. Flip a fair coin for 20 minutes. I doubt you'll even get past 10 heads in a row, let alone 100. It would take longer than the age of the universe to get 100 heads in a row. So if it happens, if it actually happened, if that's what you observed, would you say, oh, that's just rare? It's unlikely, but sure, it's a rare event. Or would you say, okay, wait a second. The only way this can realistically occur is by design. Either I designed a weighted die, or someone's playing a trick on me, or something. Okay? In statistics, as the course is going to progress, there's going to be, this is the main part of statistics is coming up. It's about testing things. I believe that the machine that I'm using in my warehouse is calibrated correctly. So I'm going to randomly take 20 pieces that I design, and I'm going to calculate their average, and I'm going to test whether or not that average is near what it's supposed to be. If it's close to what it's supposed to be, I know it's working, or I think it's working properly. But if it's far from what it's supposed to be, then I think it's not working properly. We're going to be testing things. And every time we do a test, we're going to get the result of our test. And every time we get the results, we have to ask, did this occur by chance? Or could it only have realistically occurred by design? So, an observed effect that would rarely, if ever, occur by chance is called statistically significant. And this is a big one. An observed effect that would rarely, if ever, occur by chance is called statistically significant. We will be on the lookouts for statistically significant results. Because when a statistically significant result occurs, we have to look at our data and say, okay, this should not have occurred by chance. It's too rare of an event, which means something is wrong. Either what I believe should be correct is incorrect, or something's wrong here. Statistically significant results are the ones that make us change our beliefs. If I come into a situation thinking that the average age of all people in CSUN is 19, and I take a sample and I get 17.8, I might say, well, maybe my belief is wrong. Or I might say it's close enough. So maybe I'm still right. We got to do the math for that. That's later. But the point is, if you get a result that you mathematically feel is too rare to occur by chance alone, we say it's a statistically significant result, and then we change some belief that we have about the situation. Okay, does that make sense? The idea of statistical significance is a big one. So I'd like some verbal or textual responses on this one. Does that make sense?
Yes.
That's 1, 2, 3, 4.
Yeah.
Yeah.
All right, let's pack all those yeses in. Because if the answer is no, if you don't get this one, this is a big one. The entire rest of the course, well, for the most part, will depend upon statistically significant results. Okay, so that takes us to the end of section 9.5. And now we do one more section for chapter 9. Section 9.7 is on matched pairs and other block designs. Again, there's no math in these chapters. These are very conceptual chapters. Matched pairs and other block designs. But again, these are all designs. So these are methods of doing experiments. Okay, so a matched pair design is an experiment that compares two treatments where each subject receives both treatments, and usually in a random order. So here's an example. First write it down. So suppose I'm interested in whether or not a certain task is more easily done with your left hand or your right hand. Would it make sense to get 100 people and have them use their left hand, and then 100 people and have them use their right hands and compare the results? Or would it be better to have the same 100 people use their left and their right hand? Which is a better design for this particular example? 100 people left and 100 right, or the same 100 left and right? So in this case, it's the same 100 for left and right, because it removes one extra factor that's some people are more ambidextrous than others. So randomly 100 and randomly 100 for left hand and randomly 100 for right hands. You know, it's, yeah, you can do an experiment that way. But if I really want to test whether there's a difference between left-handed and right-handed, I should use the same people for both. So it's a matched pair design. I'm matching the pairs up. Left hand, right hand, left hand, right hand, left hand, right hand. A matched pair design. We're going to see in later chapters that the mathematics of matched pair designs is a little easier than comparing two different samples. Okay, but it has its own category, which we will have to consider. A block is a group of individuals, that are known to be similar in some way. That is expected to affect the response to the treatments. So what would be an example of a block? Give me an example of an experiment where a group of people might be that might have similar characteristics to the point that they would be different than another block in the same experiment. And there's no one answer to this. You know, there's lots of examples. Can anyone think of one?
The individuals all have like the same disease or something, and they all use like a new medicine and see how it affects them.
So you're testing some medication, and a block would be all the people who have a certain condition. They
Yeah.
Okay. I saw someone write an age block. Maybe I'm testing whether or not I don't know, alcohol consumption, gender blocks, certainly. Age blocks. Yeah, there's many situations, many experiments where you might feel that if you just completely randomize it, you'll be lacking some factor like age or gender or this or that. So in those situations, I might use a block design. A block design is a random assignment. I always want randomness. Is a random assignment of treatments or a random assignment of individuals to treatments carried out within each block. Carried out within each block. So if I'm testing some drug and I think that females might have a different response to males, I might block it and look at females and males separately. Perhaps I might feel that age might be a factor. I think of the COVID vaccine, right? When the COVID vaccine first came out, and I think still now, is it for everyone of every age? What's the COVID vaccine for? Who gets it? Is
Ages
everyone-
12 and up.
Say again, was what?
Ages 12 and up.
Ages 12 and up. So obviously, age can be a factor when it comes to that as well, correct? Yes, no? Right? Right. Hope it's right. Okay. So anyways, chapter 9 is now over. Very qualitative chapter. Not a lot of math, if any, just words, definitions. As you're going to see in the homeworks, there's no math in this chapter. It's just lots of definitions. So now we're skipping ahead to chapter 15. And this is where the statistics of the class really starts. 15 is where it really begins. Up until now, definitions, simple definitions, simple examples, means, variances, IQRs, outliers, scatter plots, regression. I'm not saying none of that's important. Obviously it is. But at the end of the day, the heart of statistics is I'm interested in knowing something about my population. The average age, the average weight, this, that, something. I don't know it. If I knew it, I'd be done. I don't know it. So what am I going to do? I am going to take a sample. And I'm going to get something from my sample. And from my sample, I am going to make a conclusion about the entire population. I want to infer from my sample to my entire population something. Okay? This is the goal. So chapter 15 starts us on this journey. So chapter 15. Sampling distributions. Okay. So first, even though I said it's going to be very mathy, we still have some definitions now and again, and we're going to start with one right off the bat. This is an important distinction. A parameter. A parameter is a number that describes some aspect of the population. A parameter is a number that describes some aspect of the population. In practice, that number is not known. What's the average height of every person on the planet? No idea. Even if I wanted to. How many people are on the planet? Like what, 8 billion? How exactly would I find the average height of 8 billion people? Right? Impossible. So it's a parameter that I don't know. I want to know it. So how do I do? What do I do? I form a statistic. Okay. I form a statistic. A statistic is a number that describes some aspect of a sample. In practice, the goal is to estimate a parameter from knowledge of the statistic. So for example, if I want to know the average height of every CSUN student, I sample 1,000 CSUN students, and I get 5'7" and a half. Can I conclude definitively that the average height of every CSUN student is 5'7" and a half? No, my sample. Can I conclude that the true value is probably somewhere around 5'7" and a half? Seems reasonable. How far from 5'7" and a half can I go before I would say, no, no, too far. It's got to be between these two numbers. Now, I'm not looking for an answer here. That it's not in this chapter. It's coming up soon, but I'll describe it now. A confidence interval. This is coming later, but I'll say it now. A confidence interval is an interval of numbers that I have high confidence of the parameter being in the interval. I'm not sure if that was correct in English or not, but hopefully you all get the gist of what I'm saying. Okay, a confidence interval. If I got 5, 7.5, I might say I'm fairly confident that it's between 5, 6.5 and 5, 8.5. It's an interval of numbers where I can say I'm really confident that it's in here versus not so confident that it's out there. If I got 5, 7.5, would I say it's probably about 6.5? No, 6.5 is way out. I would not be confident that it would be 6.5. But an inch and a half in either direction, I might have high confidence. We can compute confidence intervals, and we will compute confidence intervals. We need to know specific things. How big the sample is. We have to know how confident we want to be. We want 90% confidence, 95% confidence. We want to know whether or not it came from an SRS, a simple random sample. So there's a mathematical way of computing it. And in fact, your TI-84 will do it for you. So what's really nice is we don't even have to do it by hand. The TI-84 will do it for us. Half of the statistics course, when it gets to the real stuff, is on confidence intervals. The other half is on something called hypothesis testing, which we'll get to later. And so for now, we have parameters and we have statistics. So first, any questions on that so far? The difference between a parameter and a statistic. So we will use the Greek letter mu to denote the population average. And X bar to denote the sample average. We will use sigma to denote the population standard deviation. And S to denote the sample standard deviation. Okay? With me so far? Okay. So that was section 1 on parameters and statistics. I should come up here. I always forget to do this, but 15.1 is on parameters and statistics. Section 15.2. Is on statistical estimation. And the law of large numbers. and the law of large numbers. Statistical estimation and the law of large numbers. Here's the basic idea. If I flip a coin once, what do you think I'm going to get? A pair of coin.
Well, it's a 50-50 chance, so
Yeah, it's a 50-50 chance, right? You can't really say one way or the other, right? You're just as likely to get a heads or a tails. So you flip it, you get a heads. Now you flip it a second time. What are you more likely to get, heads or tails?
Still be 50-50.
Still be 50-50. The coin has no memory. The coin does not remember, oh, last time I was heads, so I better have a tails this time to balance. Or, oh, last time I was heads, so let's keep it going. Right? Coins have no memory. Dice have no memory. Anything left to chance has no memory, correct? So every flip, it's exactly the same as the previous one. In this case, it's just as likely to be heads or tails. Agreed? So if you flip it 10 times, is it possible that you would get 5 heads and 5 tails? How about 6 heads and 4 tails? 7 heads, 3 tails? 8 and 2? 9 and 1? 10 and 0? Unlikely, but it's certainly possible, right? It's only 1 in 1,000, by the way. To get 10 heads in a row is 1 in 1,000. Remember earlier I mentioned flipping a coin till you get 100 in a row? Getting 10 in a row is 1 in 1,024, which means approximately you would need to do it 1,024 times before it happened once. But it's certainly possible, right? Now, if I asked you to flip a coin 100 times, do you think you'd ever get 100 heads and 0 tails if it was really fair? Do you think that would ever occur? 100 heads, 0 tails on 100 flips of a fair coin. It would never happen, ever, ever, ever. Your whole life you could spend waiting for it, and it would never happen. Unless, of course, there's some greater design. Either it's a fake coin, a 2-headed coin, or a weighted coin. Or, you know, if God came down, if you believe in that sort of thing, if not the great turtle in the sky, whatever, but whatever you believe, if, you know, some design says, I really want there to be 100 heads, then, you know, anything can happen in that sense. But left to their own chances, it would never occur. So here's the amazing thing about statistics. I cannot tell you with any certainty what's going to happen on any individual flip. But I can tell you what will happen in the long run. If you do it over and over and over and over and over again, then I will have roughly 50% of each outcome. So while I can't tell you anything about one flip, I can still tell you what will happen after lots of flips. This is the law of large numbers. All right, so the law of large numbers. One of the most important properties in stats, the law of large numbers, says if we draw observations at random, if we draw observations at random from a population with finite mean mu. Then, as the number of drawn observations increases, the mean X bar of the observed values tends to get closer and closer to mu. A lot of words, so make sure you understand what it says. You all with me? So if you take a sample, you get a sample mean X bar. That sample mean could be anything. But as the sample size gets larger and larger and larger, then your X bar will change because you're averaging more and more values. And that X bar is going to get closer and closer and closer to mu, the unknown mu. Now, anyone know from more advanced math classes than this one what tends to means in this context? Tends to get closer and closer to mu. Anyone know what tends to means in the language of more advanced mathematics?
Would it be like limit?
Yeah, exactly. So if those of you who've had calculus, when we say tends to get closer and closer, we mean the limit. As the sample size goes to infinity, it converges to mu. So again, this is a non-calculus based course that uses calculus based ideas. So it's always nice, at least for me, to throw them in there whenever they occur. Okay, so this is the law of large numbers, which is arguably the most important law. And it is proven, by the way. It's not just an idea. You can prove this mathematically in statistics. So let's just do a quick example. Suppose you have some population. Suppose a population exists with mean mu equals 25. Now remember, in practice, we'll never know mu, because if we knew mu in practice, then you wouldn't need to take a sample to find it, right? The whole point of taking a sample, we want to know what the average is, but if we know it, why do anything? But suppose we have a population where there's a mean of 25, and we happen to know that behind the scenes, okay? So suppose we have the following situation. If we take 2 observations, then X bar, and I'm going to put a subscript 2 there to indicate that it's an average from 2. Could really be anything, but let's suppose that my 2 results, right? So this is just as an example. So suppose my 2 results were 28 and 40. Then my average is 34. if I did X sub 1,000 bar? In other words, I took a sample of 1,000 individuals. What do I think my average? Give me a number that seems reasonable for the average of 1,000 data points. Well, Luis, what is the actual mean of the population? Hold on, guys, hold on. What is the actual mean of the population? 25. So do I expect my sample mean, which is the mean of the sample, do I expect that to be in the vicinity of the actual mean? Why is the answer no to that one? Luis, why is the answer no? This is for everyone. Where are you guys? Speak up. Speak up. The full number is not given. What do you mean by the full number is not given? What does that mean?
I think it should be close to the mean.
I think it should be close to the mean. In fact, what does the law of large numbers say? As the number of drawn observations increase. So Luis, if the mean is 25, then if I take 2 data points, it could really be anywhere, because 2 data points, any data point can be anything for the most part. So if I get 28 and then I get 40, I average them, I get 34. But if you take 1,000 observations, that's a very large number of observations. So the law of large numbers says, as you take lots and lots and lots and lots of observations, the sample average should be in the vicinity of the actual average. And the actual average is 25. So where do you think the average of 1,000 observations should be? Give me a number that you think might be reasonable for the average of 1,000 observations. Anyone, give me a number that's a reasonable value for the average of 1,000 observations. Again, 950 is nowhere near, okay, 27, 25, 24. These are close to the average. 24.5, probably the best one yet. 24.999999. So yeah, so if I said, 24.8 as an example, I would not be very shocked. That's fairly close to the true value. 950 is nowhere near 25.
All right, thought you meant like, I didn't realize we were still referring to like the mean of 25.
Ah, so what do you think I meant?
I'm kind of confused. I thought you meant like, what would the mean be? I don't know. I was confused.
Does it make sense now though? Yeah? Flower, does it make sense?
Yes.
Okay, so again, if the number of observations gets large, I would expect my sample average to be in the vicinity of my actual average. That is what the law of large numbers says. Now, section 15.3. Sampling distributions. Suppose you take a sample of size 10. So here, let's do an example here, the same example. So a population exists with mu equals 25. If you took a sample of size 10, give me a value. I want everyone to type in a value in the chat box of a reasonable mean of a sample of size 10 that comes from a population where mu is equal to 25. Keep in mind that 10 is not really a very large number in the grand scheme of things. And just so you understand what these numbers are referring to, they are referring to a test to determine whether or not wine smells bad. And the numbers are micrograms of a certain chemical per liter of wine. So the average person would be able to sense 25 molecules or whatever it is or 25 grams per liter of wine. So 40, 32, 30, 35, 35, 34. These are all reasonable. They're all larger than 25, which is interesting, right? I would think that some samples will be less, some samples will be more. But the point is, and notice that for the most part, everyone's guesses were different. Which means that we don't know in advance what we're going to get, do we? Do we know in advance what the outcome of our sample is going to be? No. So not only do we not know the true value usually, we do here, but usually we don't know, but every sample will provide a different X bar. And when I say every sample, I'm not saying it's not possible for two to be the same, but for the most part, every sample will provide a different X bar for the most part. Which means I might ask the following question. What's the likelihood that my X bar will have some number? What's the likelihood that X bar will be 24.3? Or that X bar will be 26.1 or 29.2? Just like I might ask what the likelihood of any one result would be, so just like I might ask the likelihood of any one result, I can also ask the likelihood of X bar. What's the likelihood that X bar is 25 or 23 or 22 and so on? So what I want to do now is I actually want to take you back to something that we've done before, applet central limit theorem. So can you all see this? Just to make sure I'm still sharing my screen. You all see this, correct?
No.
No, you don't, or you do?
We
You're
don't.
sharing the note screen.
Ah, that's right. I should probably change that. Thank you. Okay, so stop sharing this and start sharing this. Okay, so that's better, right? Okay, so here we have something that's labeled as a central limit theorem, but again, let's not worry about that. That'll come later. Let's suppose I have a situation where I'm taking one at a time. Sample size 1. So pick one of these shapes. One of the, I don't care which one. Give me a number from 1 to 8. Which one?
6.
6. Okay. So 6 says, if I take one at a time, I'm pretty likely to be around here, less likely to be here, a little more likely to be here, and really unlikely to be on the edges. Right? That's what the shape of 6 is, correct? So let's say I take like a sample of size 1,000, and I look at them one at a time. How many times will I get every number from 0 to 100? If numbers 25 to 30 are really likely, and 50 is somewhat unlikely, and 60 is a little more likely, what do you think the shape of my distribution is going to be if I take a really large sample? How often would I get 1 or 0 in the grand scheme of things?
Once.
Well, maybe not once, but a small amount of times, correct?
Yeah.
Right? So let's actually go ahead. 30, no, not often, right? So let's go ahead and actually perform this experiment. We'll take lots and lots and lots of observations. And this is what we get. We took 100,469 observations. And we got 0 or 1 very few times. Lots of these, less of those, a little bit more of those, and they kind of tapered off. Does that seem a likely result based upon the shapes of my distribution? Yeah. Okay. Seems very likely, right? Now, suppose instead, actually, I want to do a different one. You picked 6, which is great, but I want to do 4 because it's easier for me to demonstrate what I'm going to say next. So let's redo it for number 4. How often do I think I'm going to get very low numbers, middle numbers, and high numbers if the shape of my distribution looks like this? What numbers do I expect to get the most of if my distribution looks like this?
100.
Sorry?
And 100.
One more time, I didn't hear.
0 and 100.
Okay, so yeah, someone said low and high numbers, right? So let's actually go ahead and do it, and let's see what we get. Does that seem like it's what we expected? Yeah, right? Okay, so now I have a follow-up question. This was a little tougher to answer. Suppose instead of looking at 1 at a time, I took 2 at a time and I averaged them. And that's what I recorded. I didn't record each individual observation. I took 2 observations at a time, averaged them, and record that. Which numbers do you think would occur the most if I did it 2 at a time instead of 1 at a time? Do you think I'd get lots of 0s or lots of 100s if I took 2 at a time and I averaged them? How about numbers right in the middle? If I took 2 at a time and I averaged them, do I think I get a lot of numbers in the middle? You don't think so, huh? Well, Leanne, let me ask you a question. Hold on, someone texted something. No, okay, I want you a question. If I take 2 at a time, do you think I might get 2 low numbers quite often? Low numbers being very popular. Do you think if I did 2 at a time, I get lots of pairs of low numbers? And if I got lots of pairs of low numbers and I average them, would it give me a low number?
Yeah.
Yes, right? If you gave me 2 low numbers and I average them, it would give me a low number. What if I got 2 high numbers and I average them? Would it give me a high number?
No.
Like 100 and like if I got 198 and I average them, what would I get?
Probably a lower number.
Wait, 1 second. What's the average of 198?
I don't know.
You don't know the average of 198? Yes, you do. Yes, you do. Don't look at your calculator. What's the average of 198?
Don't you have to like add up all the numbers and divide by?
Okay, so add them up and divide by how many do I have? What's the average of 198? Yeah, you're on the hot spot now. Come on. Add them up and divide by 2.
Don't you have to add like each individual number with?
Yes, but there's only 2 numbers. 198.
Oh. Okay.
Sorry?
I said okay.
Okay, so what's the average of 198? You got this, girl. I believe in
I
you.
don't know. I don't forgot how to like. Use it.
You forgot how to add 2 numbers and divide by 2?
Well, 198 divided by 2, is that all that it is?
Yes.
Oh, so it's basically 200 divided by 2. So it's like
Yes.
16. Okay, sorry. I don't know. I thought you had to do something else.
So I ask again, if you give me 2 big numbers and you average them, do you expect to get a big number?
Yeah.
Yes.
Yeah. Okay.
Right. Now, how often in the grand scheme of things, if you get 2 numbers, will you get 1 small and 1 big? Remember, the small numbers are very likely. The big numbers are very likely. So do I often? I expected to get a small number and a big number often. Almost as often as 2 smalls or 2 bigs. Correct? And if I average a small and a big, what would I get? If I average a very small and a very large number, what would I get? I get a middle number. So I expect if I do 2 at a time to have lots of averages here, lots of averages here, and lots of averages here. Let's go ahead and do it. I just took a sample of 83,980, and I got numbers in the middle more often than anything else. I got relatively large numbers pretty often and relatively small numbers pretty often. The numbers in the middle occurred the most. Does that make sense? Seem reasonable based upon the original distribution? When you take more than 1 at a time, we call that a sampling distribution because it's coming from a sample. Not just 1 at a time, but a sample of large numbers. Now, if you did 3 at a time, what do you think it might look like if I did 3 at a time? Hard to guess, hard to predict, right? Let's do 3. I can't really say I would have predicted that. What about 4? Nah, still not sure I would have predicted that. Let's go up ahead to 10. Well, wait a second. Wait a second. That looks very familiar. What is that? That's a bell curve. Interesting. Let's do a different one. Let's do something like 3, 1 at a time, which looks very strange. Lots of small numbers, some big numbers, not really a lot here. And let's do samples of size 10. Ooh, ooh, what? What is that? What is that? You're not oohing and ahhing enough here, guys. This is like crazy stuff. This is like, what? That's statistically significant. That's what you should be saying. Okay, it's another, yes, speechless. That's what I'm going for. Even 2. Look at that. That's 2. Yeah, oh my goodness, that's right. That's what I'm talking about. I don't know what that means, but yes, the rest of them are great. And if we go to 10, what? Another bell curve? OMG. It's like no matter what we start with, no matter how weird it looks when we start, if we make the sample size large enough, it looks like a bell curve. Anyone know by any chance? Can anyone guess what that theorem is called in statistics? Can anyone guess what that theorem is called in statistics? Just throwing that out there is something. What do you think?
Central limit
Oh
theorem.
my God, how did you figure that one out? It's crazy. Wow. Yes. Now, of course, we're not yet at the central limit theorem, but when we get there, it's going to be mind-blowing, like awesome. The point of this section that I'm trying to make, based upon what we just saw there, is that the original data has some distribution, but when you take samples, you get a different distribution called the sampling distribution. As we saw in the first example, every time we increased it by 1, the shape changed. Sampling distributions depend upon the number in the sample. As we're going to see, the central limit theorem says if the sample is large enough, it'll look like a bell curve no matter what. But we didn't get there at n equals 1 or 2 or 3 or 4 or 5. It took a while for us to get there. We skipped ahead to 10. I think it was number 4 we did, right? By the time we were at 5, this not quite a bell curve, but I can kind of see it being close. 6. 6 is not horrible. Already by 6, it's almost bellish. I don't know if that's a word, bellish. Sounds like a Twilight thing. But anyways, the point is that the central limit theorem says that as the sample size gets larger, the sampling distribution will look like a normal distribution. But the idea right now, the point I'm trying to make, is that sampling distributions are different than the population distribution. So, important. The population distribution is the distribution of values of the individuals, of values of the variable, I'm sorry, I skipped the part, of the values of the variable among all the individuals in the population. When you look at them one at a time, one at a time. The sampling distribution of a statistic, the sampling distribution of a statistic, X bar, not mu. Mu is known, mu is fixed, mu is a constant. I just don't know what it is. X bar is a statistic. It's from my sample. It's a different value every time. The sampling distribution of a statistic is the distribution of values taken by the statistic when considering all possible samples of some size. from the population. So again, the population distribution just looks at them one at a time and says, how likely is it to be this? How likely is it to be this? How likely is it to be this? And you have your shape, you have your distribution. The sampling distribution is for the statistic, usually X bar, usually the average. And it says, how likely is X bar to be this, or X bar to be that, or X bar to be this, among all possible X bar values that you might get. That shape will in general be different than the original shape. The population distribution and the sample distribution will not always be the same size or the same shape. As we saw, the sampling distribution changes as it increases, becoming normal, although that will be later in this chapter. In fact, we'll do it on Thursday. Okay. So are there any questions on what we covered today? Not very mathematical, very conceptual, but a lot of important stuff. Are there any questions on any of it? All right, so hopefully you ruminate on this and you really think about it. It's really some amazing stuff. And we'll stop here because I want to talk to a few people, and I will see you guys on Thursday.